Here on problem 2, I have this big long explanation here, fancy looking equations, but really all it is a way of saying that we can find the greatest common divisor, the GCD, by using the prime factorization. If we write the prime factorizations of two numbers a and b out like this in terms of primes p1, p2, all the way out to pk, then the greatest common divisor of a and b is going to be that same list of primes. Now notice I've got the same list of primes in both prime factorizations. It's that same list of primes, but raised to powers which are the minimum of the powers that they were raised to for either a or b. So for example, for a, prime number 1 was raised to the a1 power, and for b, prime number 1 was raised to the b1 power. Well, to help form the greatest common divisor, we're going to raise p1 to the minimum of a1 and b1. And notice that if the list of primes in the prime factorizations for a and b aren't the same, we can always make them the same by adding some zero powers of the primes that we need. And here's an example of that. A is 2 cubed times 3 times 5 squared, but b is 2 squared times 3 to the 4th times 7 cubed. Well, a doesn't have the 7 in it, and b doesn't have the 5 in it, but we can make them both the same by adding a zero power, or multiplying, more properly, multiplying by a zero power of 7 for a, and a zero power of 5 for b. Okay, well, enough of that. Let me show you the solution here. I'm going to write out prime factorizations for all these numbers. So in part A, 21 is 3 to the 1 times 7 to the 1. Okay, 45 is 3 times 15, which is 3 times 5, which is 3 squared times 5 times 7 to the 0. And 21 is 3 to the 1 times 5 to the 0 times 7 to the 1. And now I can say that the GCD of 21 and 45 is 3 to the 1, which is the minimum of 1 and 2, times 5 to the 0 times 7 to the 0, which is 3. Okay? And here you can see me taking the minimum. For the power of 3 in the GCD, I take the minimum of the 1 and the 2. For the power of 5 in the GCD, I take the minimum of 0 and 1. And for the power of 7, I take the minimum of 1 and 0. And this is, indeed, the greatest common divisor of 21 and 45. For part B, I'll just go a little bit more quickly through the remaining parts. 66 is 2 times 33, which is 3 times 11. And 90 is 3 times 30, which is 3 times 10, which is 2 times 5. And so the GCD of 66 and 90 is 2 times 3. There's a single 2. There's a single 3 that's common and a single 2 that's common. And there's no others that I could circle like that. So the GCD is in fact 6. For part C, 14 and 30. 14 is 2 times 7. 30, I just did up here, didn't I? I guess not. It's 2 times 3 times 5. And so the GCD of 14 and 30 is 2. Okay, we can only circle one common prime number in the prime factorization there. Finally, for part D, hopefully I have enough room, 120 and 126. 120 is 2 times 60, which is 2 times 30, which is 2 times 15. 126, on the other hand, is 2 times 63, which is 3 times 21, which is 3 times 7. If I haven't made any mistakes in all of this. Green pen, and I can circle the 2, and I can circle the 3, but nothing else. And so the GCD of 120 and 126 is 2 times 3, which is 6. Okay. Yeah, if 6 goes into 120, it also goes into 126, right? But 12 would be the next one you might think of. 12 goes into 120, but it doesn't go into 126. So 6 makes sense to me here. Okay, that's the method of prime factorizations for finding greatest common divisors. It's not the greatest method, and we'll study the Euler method, or the Euclid method next.